All right, let's get into derivatives of trig functions. And what I'm going to do here is I'm going to, if the function f of x is the sine of x, what we're going to do is we're going to prove that its derivative is the cosine. Okay, so what we're going to do is we're going to use the definition of the derivative, right? So the derivative is limit as h goes to 0, f of x plus h minus f of x all over h. So this will become limit as h goes to 0, f of x plus h. So we'll have sine of x plus h. Remember, sine of x is our original function, minus the sine of x. This is all over h. And now, hopefully you may remember the sine of u plus v rule is the sine of u cosine v plus cosine u sine v. So I'm going to use that with sine of x plus h. So this derivative ends up being limit as h goes to 0. I've got sine x cosine h plus cosine x sine h. And then I still got this minus sine of x on the end. This is all over the h. Okay. And what I'm going to do is I'm going to take a sine of x out of those two terms. And I have cosine of h minus 1. And then over here I've got cosine x sine h. Okay, and this is all over h. Okay. And now what I'm going to do is I'm going to split these up. Is that a common denominator? And I'm looking at, hopefully you're kind of seeing this right here. If you remember your special trig, limit as h goes to 0 of sine of h over h, that's 1. Okay, so I'm going to use that right there. And then if you're looking at this one right here, this is pretty close to, let me write the special trig limit here. The limit as h goes to 0 of 1 minus cosine h over h. This is 0. So what I'm going to do is I'm going to take a negative out of that. So I'm going to write this as limit as h goes to 0 of the sine of x times limit h goes to 0 of, I'm going to take a negative out of this. So I have 1 minus cosine h over h. And then over here, I have limit h goes to 0 of the cosine, whoops, I'm sorry, that right there is supposed to be an x. My apologies. That's cosine of x. Make that an x right there. Times limit h goes to 0 sine h over h. Okay, well, we said this is 1. So that's 1 right there. Limit as h goes to 0, cosine x is just cosine x. This part right here is negative 0, so just 0. This is sine of x times 0. So I got sine of x times 0 plus cosine x times 1. That's just the cosine of x. So the derivative of the sine is the cosine of x. So we just proved that the derivative is the cosine. Okay, so that's the process. It would be very similar if you are taking the derivative of the cosine, except you'd get a different result. Okay, so here's your two rules. Derivative of the sine is the cosine. Derivative of the cosine is negative sine. Again, very similar to prove that as well. We won't go through that proof in here, but let's go ahead and use that information now. Let's go ahead and take some derivatives. Here's the first one. Derivative of 4x, 4 times 1, minus 5. The constant stays there, but I say, hey, what's the derivative of the cosine? Negative sine. So the overall derivative is 4 plus 5 sine of x. Let's do it with theta now. F of theta. And I'm going to go ahead and let me rewrite this before I even do the problem. I have pi sine of theta plus 1/3 theta to the negative 1/2. So I can use my power rule on this, right? Let's go ahead and find the derivative. Pi is a constant, it stays there. Derivative of the sine is just the cosine. 1/3 stays there. Now we take the power rule. So the negative 1/2 goes in front. Theta will now go to negative 1/2 minus 1, which is negative 3/2. Okay. And so this derivative, once we clean that up, is pi cosine theta minus 1/6 theta to the 3/2, right? Theta to the negative 3/2, take that down and make that theta to the positive 3/2 using the rule of a to the negative m is 1/8 of the m, right? All right, let's keep going here. It looks like on this one, I'm going to have to use the power rule here with theta squared and the sine of theta. I'm going to have to use the power rule when I take that derivative. So f prime of theta. So I say, well, the derivative of the first one, derivative of theta squared is 2 theta. Derivative of the first times the second, so the second stays the same, plus the first, so theta squared stays the same. Now I take the derivative of the sine theta, which is cosine theta, right? And then we do this one, minus 3, derivative of the cosine, negative sine. So f prime of theta is 2 theta sine theta plus theta squared cosine theta plus 3 sine of theta. All right, let's keep going, and instead of with the function notation, let's use Leibniz's notation with dp dq, right? So here's my p. I'm going to have to use the quotient rule. So I'm running the derivative with respect to q on both sides. D dq. This is again Leibniz's notation here. So I have dp dq, so the derivative of p with respect to q is, so I take the derivative of the top times the bottom minus the top, derivative of the bottom, all over bottom squared, right? And then we just clean this thing up. So we got negative q cubed sine q minus 3q squared cosine q. This is all over q to the 6th. I would go ahead and take a q squared out. So I can say, okay, q squared over q to the 6th, that leaves me with q to the 4th. So dp dq is negative q sine q minus 3 cosine q. This is all over q to the 4th. And that's as far as you can go on that. Let's do another one with Leibniz's notation. R equals, and another quotient rule involved here. So I'm going to take the derivative with respect to theta, derivative with respect to theta. So dr d theta, this is like r prime, right? This is the same as r prime equals, right? The derivative of r. So dr d theta equals derivative of the top is negative sine. That's the derivative of the cosine. Derivative of the top is negative sine times the bottom, leave it the same, minus the top. Derivative of the bottom, well, the derivative of 1 is 0, derivative of the cosine is, oh, I'm sorry, derivative of the sine is cosine, so it's just a cosine right there, all over bottom squared. So dr d theta ends up being negative sine theta minus sine of squared theta. I'm going to distribute that, or actually that's negative cosine times cosine, so minus cosine squared theta. Now remember, sine squared plus cosine squared is 1. So let me take a negative out of this, sine squared and the cosine squared. So I've got negative sine of theta minus, and this, again, this ends up being 1. And then notice, hey, if I take a negative out, I would have sine theta plus 1, which will cancel with one of those 1 plus sine thetas on the bottom. So that will cancel and just give me one of these left down here. So dr d theta just ends up being a negative 1 over 1 plus sine theta in the end. Derivative of r with respect to theta. Well, there is a rule for the tangent, but let's imagine you didn't know the rule for what the derivative of the tangent is. Then you say, well, I know tangent is sine over cosine. So if I was finding dy dx or y prime, I could just run the quotient rule. The derivative of the top times the bottom minus the top, derivative of the bottom, which is negative sine, derivative of cosine is negative sine, over bottom squared. So I have cosine squared plus sine squared all over cosine of x quantity squared. Well, sine squared plus cosine squared is 1. So the derivative is 1 over cosine times 1 over cosine. That's secant times secant. That's secant squared. So what's the derivative of the tangent? Secant squared, right? So you could just do that if you wanted to. Same thing for the cotangent. You do the same thing. If you took the derivative of the cotangent, you'd get negative cosecant squared. If you did the quotient rule with 1 over cosine, you would get secant tangent. If you did the quotient rule with 1 over sine, you'd get negative cosecant cotangent. So those are the derivatives of the other 4 trig functions. So as long as you know what the derivative of the sine is, and you know the derivative of the cosine is, you really should know the other ones if you can run the rule, right? So, but let's apply this. Let's go ahead and, if we have secant over x, let's go ahead and find that derivative using the quotient rule there. So the derivative would be derivative of the secant, derivative of the top, derivative of the secant, secant tangent. Derivative of the top times the bottom, minus the top stays the same. Derivative of x is just 1. All over bottom squared, right? And so we have, if I take a secant out of both of those, I would have x tangent of x minus 1. And this is all over x squared. And that's really all as far as I can go with that one there. This one I would actually simplify a little bit before I did it. You know, I have cosine plus 2 sine, but it's being multiplied. So I have sines and cosines, but the cosecant's 1 over sine. So why don't I go ahead and distribute that through? So I have cosine over sine. Well, that's cotangent. And then 2 sine over sine. That's just a 2 plus 2, right? Because, again, the sine over the sine cancels. So I just have, here's my original function, cotangent plus 2. So then I just take the derivative of the cotangent, and I say, well, what's the derivative of the cotangent? I look up here, and I say, oh, yeah, that's negative cosecant squared. Negative cosecant squared x. Derivative of 2 is 0, so plus 0 on that. Notice this problem says find the second derivative on this. So if y equals negative 3 secant of x, the first derivative would be negative 3 stays there. I take the derivative of the secant, and that's secant tangent. Okay, there's the first derivative. But we want the second derivative. So now I'm going to have to do this with the product rule to take the second derivative. So I say derivative of the first, which is negative 3 secant. So that'd be negative 3 secant tangent. There's the derivative of the first. Tangent stays the same times the second. Plus the first stays the same now. And then times the derivative of the tangent. Well, the derivative of the tangent is secant squared. Okay, so we got negative 3 secant tangent squared minus 3 secant cubed x. I guess I could take a negative 3 secant out and have tangent squared x plus secant squared x. And then I go a little further. You know, the tangent squared, if I want to put this all in terms of secants, remember 1 plus tangent squared is secant squared. So secant squared minus 1 is tangent squared from the Pythagorean identity. So I get secant squared, 2 secant squared x minus 1. That's really as far as I can go for the second derivative on that. All right, determine the point at which x plus cosine x has a horizontal tangent on 0 to 2 pi, right? So I'm looking at this thing like, I don't know what this looks like, but I'm like, you know, where does it have a perfectly horizontal? On this one that I drew, which again is not what it looks like, those would be my spots that I'm looking for, but I'm only looking from 0 to 2 pi. I'm only looking within that, right? That's what we're doing algebraically, is where is the slope? 0, right? The slope of the tangent, 0. Well, the slope of the tangent line is the derivative, right? So we got to find the derivative first. Here's our function. Let's find the derivative. Derivative of the cosine is negative sine. And where is the slope of the tangent equals 0, right? Where's the derivative equals 0? Let's add sine to both sides. So sine of x equals 1. Well, the sine of what equals 1? I look on my unit circle. I'm like, oh, it happens at pi halves. All right, so I didn't draw this very good. It only happens at pi halves. Well, the next spot it would happen, it would be 5 pi halves, 9 pi halves, and so on. But those are outside the what we're only looking between 0 and 2 pi. So the only one we're concerned with is at pi halves, right? So at x equals pi halves is where it happens. In fact, let's take this a little further here. You want the point. So point, well, we know that this is the x value for where it happens. Here's my function. So y of pi halves would be pi halves plus cosine pi halves. So pi halves, we know cosine pi halves is 0. So y of pi halves is pi halves. So it's at the point pi halves, comma pi halves, right? So again, whatever this looks like, yeah, that's terrible too. Maybe it's like this, right? But this happens right at pi halves, and the y value is also pi halves, okay? So it has a slope, the tangent there. Maybe I'll pull up Desmos so we can look at it after. Let's actually take this a little further. Let's write the equation of the tangent line. What's the equation? What's the equation of the tangent where the has a horizontal tangent? In other words, the slope is 0. So we know the slope is 0. We know I have the point pi halves, comma pi halves. Y minus y1 equals mx minus x1. So y ends up being pi halves. And let's just actually pull up Desmos and show you this with a nice graph of it, x plus cosine of x. Oops, that's not right. Come on. Okay, here's our x plus cosine x. Maybe let me put it in and have it steps be like pi halves kind of deal. So you can see it every pi halves. So we're only looking from the 0 up to 2 pi. And I'm going to put that point in pi halves, comma pi halves. And let's label that. That's where it happens. And we said the equation of that is y equals pi halves. That's that green horizontal tangent line. I'll give you a nice little look at that for that problem. That's that point at which it has a horizontal tangent, and we actually wrote the equation of the horizontal tangent. Well, thanks so much for watching and taking notes. We'll see you next time.